In this video, we will continue our discussion of substitution and elimination reactions. I know you thought it was over, but it's not. So we're going to dig deeper into alcohols and substitution and elimination reactions, and then we'll think a little bit about how amines can be involved in these reactions as well. We'll want to predict products, including stereochemistry, or we may predict reactants or reagents for substitution and elimination reactions of alcohols and also amines. We will explain some problems associated with the substitution and elimination reactions of alcohols and also amines under the conditions that are used for alkyl halides. We will learn how to turn hydroxide into a good leaving group. We will learn something called the Williamson Ether Synthesis and start to think about synthesis problems. This is going to be exciting right here. And then again, we will finish up with the discussion of amines. So you already know about alcohols as substrates in SN1 and E1 reactions. And if you need a little bit of a refresher, I have posted a short video of review, so you should check that out first. But now that we remember that alcohols can undergo E1 reactions when treated with concentrated sulfuric acid or phosphoric acid, and SN1 reactions when treated with HX, where X ends up coordinating at the end to make the substitution product. So it coordinates to the carbocation. And now that we have reviewed that we need to be aware of rearrangements, let's think about whether or not alcohols can participate in E2 and SN2. Why not, right? So the question here is, can we use alcohols in all substitution and elimination reactions? What do you think? All right. Well, let's think about what would happen. So we would like to treat this tertiary alcohol with hydroxide. Hydroxide is, as we know, a strong base. So this would certainly favor a fast E2. But for E2, we would like to deprotonate at the beta carbon, right? In E2, we deprotonate at the beta carbon to generate an alkene. What will happen if we treat this alcohol with hydroxide? Is it going to deprotonate the beta carbon to generate alkene? No, definitely not, right? It's not going to do that. It's going to deprotonate here. You're going to deprotonate the alcohol. You're not going to get the alkene. You'll observe the alkoxide. And that's just going to sit there and laugh at you. Ha ha ha, alkoxide. No alkene. Don't worry, there's going to be a solution. And then, so problem number one, so the OH is more acidic than CH, right? So we already know this. So that's this issue with this proposed E2 that we have. And now the second reaction is proposed SN2. So think about what we would be proposing here. Cyanide be attacking sigma star, so the non-bonding pair of electrons on carbon attack sigma star CO and displace hydroxide. So is that going to work? Is that good? No, definitely not, right? Hydroxide is not a leaving group. It's going to be a leaving group only under extremely specific circumstances that we're going to discuss in the next semester. So hydroxide is not a leaving group. How do I know? Well, we want to look at the pKa of its conjugate acid, which is water, has a pKa of 16. So what that means is that hydroxide is a strong base. It's not stable. It's a bad leaving group. All right, so is that it? Are we done with this? No. So there are solutions to these problems. Let's just recap the problems. So the two problems are hydroxide is more, OH, is more acidic than CH, and hydroxide is a bad leaving group. All right, now let's move on. So again, let's imagine that we really want to generate an alkene from an alcohol. So we want to eliminate at the beta carbon. We propose an E2, but of course we can't, that does not occur. Problem number 1. The hydroxyl is acidic. So what we really would end up getting is the alkoxide. And then, of course, we've already talked about this. I mean, even if for some reason you could deprotonate here, hydroxide is not a good leaving group. Now, we already know a solution to this. We already have a solution to this problem. It's the E1 elimination of alcohols. So the hydroxyl is acidic, fine, we're not going to use a base. We use concentrated sulfuric acid, which is a strong acid. And that addresses this second problem as well because it makes hydroxyl into a good leaving group. So we know our first step is proton transfer, and then we generate water. Again, a good leaving group. So we've already reviewed this mechanism. We have a heterolysis, generate the carbocation. And from the carbocation, the beta carbon, and there's 2 beta carbons that are equivalent, can be deprotonated to generate the alkene. Of course, we know there's a problem with this solution, right? The E1 solution to making alkenes. It's great. Like, we got the alkene. We desired the alkene. We got the alkene. But the problem is this involved carbocations. And we have spent a ton of time discussing the fact that carbocations can rearrange. So carbocations should really be avoided if possible. And I'll give you some examples today of eliminations that we can carry out with E2 eliminations that we just can't do with E1 because the carbocation would rearrange. Let's learn how to do this. Let's learn how to perform an E2 elimination on an alcohol. And there's going to be a step first before the E2 elimination because we can't have the acidic OH, and hydroxide is not a leaving group. It's just not. It's the conjugate base of a weak acid. So we have to do something first. So what we're going to do first is we are going to turn hydroxyl into a leaving group. And when we do that, it also gets rid of the acidic proton. So these are the reagents that are used. I know, you're like, what are those? Well, TSCl, this is tosyl chloride. And we have talked about tosyl before. Tosyl stands for toluene sulfonic. And I'm not going to write it out because I don't really want to, but tosyl stands for toluene sulfonic. And then the chloride is on that tosyl group. So here's your toluene sulfonic. That's your tosyl part. It's on here. TS. And here's the Cl. So TSCl, tosyl chloride. When you take an alcohol and you treat it with tosyl chloride and pyridine, pyridine is acting as a base. So let's draw the structure of pyridine. Here it is. Got that nice basic pair of electrons. You will get the tosylate. So we have start with an alcohol, we treat it with tosyl chloride and pyridine, and we get the tosylate. What essentially happens here, and I'm sorry, this mechanism, what I'm about to tell you is a little bit different than what's in the book, but I'm the boss, and I also think I'm right. So what you have happening is the alcohol does an SN2 on tosyl chloride. That generates this species. Okay, so we have this thing. This is like basically protonated sulfuric acid. This is like super acidic. Did everybody hear what I said? That is like protonated sulfuric acid. I'm going to abbreviate this aromatic ring as just AR for aromatic. So that's super duper acidic. Super acidic. It's basically like protonated sulfuric acid. That should sound crazy to you. And that's why you have the pyridine. So then the pyridine just deprotonates and you get the tosylate. And so I think you can see why I usually abbreviate the tosylate because you have this gigantic thing group hanging off of the oxygen here. So there we go. So these two things are the same thing, OTS, or you can draw it out. And what's great now is sort of two things, right? We don't have the acidic hydrogen anymore. We've replaced the acidic hydrogen with this TS, right? So the acidic hydrogen is gone. Awesome. We replaced it with TS. Problem solved. And then maybe even more importantly, we have made a good leaving group. So now OTS, it's a good leaving group. Yes, yes, yes. Awesome. So we turn it in to OTS. So now if we take this tosylate and we treat it with sodium hydroxide, we're going to have a great chance for E2 because sodium hydroxide is a strong base. And now we don't have this problem we had before. We don't have the OH, which was more acidic than the beta hydrogen. So now when we treat the tosylate with sodium hydroxide, we can just observe, we just observed an E2 elimination. Okay, so you deprotonate the beta carbon, and then you get the desired alkene. All right, so we've already talked about tosylates. I just said they behave like alkyl halides, and they do. But now you know why they're so important, and now you know how to make them. So now that we know about tosylates, let's think about another way that we might use them. So a few moments ago, we discussed that we might want to, for example, facilitate a substitution reaction. So I have here a primary alcohol as an example, and that's going to make a primary alkyl nitrile. I've proposed an SN2. Cyanide is an excellent nucleophile. Primary alcohol or primary alkyl halide would be great for SN2 because it's not very sterically hindered. But think about what we're proposing. We're proposing displacing hydroxide. Well, remember, hydroxide is not a leaving group. It is a strong base. It is a bad leaving group. Its conjugate acid has a pKa of 16. So this proposed SN2 does not happen. Hydroxide is a bad leaving group, but tosylate is a great leaving group. So I should have maybe drawn it out here, and I apologize for that. We looked at this, I believe, in one of the previous substitution and elimination reactions, but it's worth looking at it, videos, excuse me, but it's worth looking at it again. So this is OTS, and this should look a lot to you. It should look really similar to the conjugate base of sulfuric acid, right? They're really similar. The only difference is we have this alkyl group versus this hydroxyl. And it's a big difference, but what we know is that, or what we can infer is that tosylate is the conjugate base of a strong acid. Tosic acid is a strong acid. And we're going to start to use it quite a bit. So HOTS, tosic acid. So tosylate is the conjugate base of a strong acid, just like the conjugate base of sulfuric acid is. So in other words, it's stable. It's a good leaving group. Yes, awesome. So if we want to facilitate this SN2 reaction, all we need to do is turn this alcohol into a tosylate. So we'll treat it with tosyl chloride and pyridine. That will generate the tosylate. And now the tosylate is a good leaving group. Take the tosylate, and you can treat it with sodium cyanide and generate the desired substitution product. And this is an awesome SN2, right? Because cyanide is such an excellent nucleophile, and we have this primary tosylate. So this is a good rate of SN2, a fast SN2. So tosylates are really, really useful. You can use them for E2, like we just discussed. So I could take this tosylate And I could treat it with sodium hydroxide, and that would generate the alkene, the elimination product. We looked at the substitution just now with cyanide. And we're going to see we can even take tosylates, and we can even use them in SN1 and E1s if we so desire. So tosylates are a really versatile reagent. And the whole idea is you take hydroxide, which is not a leaving group. It is a bad leaving group. And we have this thing with the OH being acidic, but it's a bad leaving group, mildly acidic. And we turn it into a good leaving group. So tosylates, super useful. So let's start to think about how we might use tosylates. I would like for you to pause and provide some reagents that you think might accomplish these transformations. Okay, now the old you may have come up with something like this, so let's have a timeout. So we might have seen that we have eliminated water. It's an alcohol, so we might say, all right, well, I propose an E1 elimination with sulfuric acid. You might notice we have an alcohol. We're doing a substitution reaction. We have the alkyl bromide as the product. I accomplished this with HX. Well, spoiler alert, where X here is Br. These aren't going to work. Both of these substrates are prone to rearrangement, and SN1 and E1 are going to go through carbocations. So that's what all I have written out here. Let's look at the proposed E1 first. So you would end up with this carbocation after you generate water and this bond breaks, and that carbocation would rearrange to make a more stable tertiary carbocation, secondary versus tertiary, and we'd observe this alkene product from E1. For the substitution reaction, same idea. Once you make a good leaving group and water leaves, you generate this carbocation that has a strained ring adjacent to the cation. So that ring opens. You have this carbocation that will actually probably rearrange further, to be honest, but let's not worry too much about it. And then you get coordination. So honestly, you'd probably then end up with another rearrangement where you have a hydride shift and so on and so forth. But let's suffice it to say, it's going to be a mess. You're going to have a mixture of products. So we want substitution and elimination reactions here without rearrangements. So how do we avoid carbocation rearrangement? Well, we need to use SN2 and E2. We need to avoid carbocations. And to use SN2 and E2, we need to use tosylates because tosylates have hydroxyl converted into a good leaving group. So if you'd like to try that, if you came up with these answers and you want to try to think about the tosylate solution, now's the time to pause. So first steps for both of these reactions are that we're going to take the alcohol and convert it into the tosylate. And I'm not going to write out the mechanism here. I'm just going to show you what's called the intermediate. So the intermediate after step 1 is this tosylate. And then the tosylate will be subjected in step 2 to sodium hydroxide. And then I will go ahead and draw out the mechanism of the E2. Okay, this is just a normal E2 mechanism with this great tosylate leaving group, this nice stable conjugate base. No rearrangement, we got our desired product. When we tried to use E1, we got this funky alkene. We didn't want that. We wanted this one. The only way to get it is E2 using a tosylate. The next reaction, we do not want a rearrangement. So to avoid that rearrangement, what we do is we use a tosylate. So we're going to, after step 1, end up with this intermediate. We could get it in a bottle if we wanted to. And then we're going to treat it with sodium bromide, and we would just have a super straightforward SN2 to get the product. Cool. Tosylates are useful in synthesis. So in making stuff. Synthesis, making stuff, making complex molecules, which we'll just call stuff. But it turns out that there are other reagents that we can use if we'd like to directly convert an alcohol into, say, an alkyl bromide or an alcohol into an alkyl chloride. And those reagents, they use SN2, so it's via SN2s, but first they make hydroxide into a good leaving group. All right, so I'll show you how to do that now. Let me walk you through how this works. I know a lot just popped up on your screen, but let's take a deep breath. So we're going to start out with the alcohol. And the alcohol here is electron rich. There's a lone pair on oxygen that can act as a nucleophile. And in fact, it does. So it attacks sigma star PBr and breaks that PBr bond. Now, why? Well, oxygen and phosphorus make a super strong bond, so that PO bond is really the driving force for this entire reaction. So once it's made this delightful species, this is electron poor. You can see the positive formal charge. You displace bromide, and bromide is electron rich. So now there's another SN2, this time on carbon. So there's this SN2 on carbon to displace the good leaving group. This is a quite stable molecule that then goes on and isomerizes and does some fun stuff. But again, it has that PO bond. That's a very strong bond. And what we're actually interested in, the alkyl halide. So that's what we have written here. Now it's important to note this is an SN2 reaction at carbon. So there were two SN2s, one at phosphorus and then one at carbon. We really only care about the one at carbon. So if this were to be a chiral alcohol, we would see inversion of stereochemistry. Now we can take a look at the second transformation, which is the conversion of the alcohol into an alkyl chloride. Now I should mention in your book, Carty uses a reagent called PCl3. I have, in all my years as a synthetic chemist, never encountered that reagent. We would use thionyl chloride, SOCl2. So I would like for you to recognize both ways of converting an alcohol directly into an alkyl chloride. Either using thionyl chloride, SOCl2, and pyridine as a base, or PCl3. I think he uses PCl3 because it looks like PBr3, but again, I have never encountered PCl3 as a synthetic chemist in this context. So let's go ahead and look at this mechanism. So he has the same idea. So you have the oxygen of the alcohol initially acting as a nucleophile, as an electron-rich species, displacing chlorides. You have an SN2 on sulfur. That generates this extremely acidic intermediate, which is why pyridine is absolutely required here. It neutralizes that intermediate. So after the proton transfer, you have this intermediate, which has a good leaving group, and it is electron poor. Chlorine is your electron-rich species. Chloride is your electron-rich species. It comes in and does an SN2 on carbon. So again, if this were a chiral alcohol, we would have inversion of stereochemistry. When chlorine does that SN2 on carbon, it displaces chloride, which is off of sulfur, which is a good leaving group, but it also makes sulfur dioxide, which is a gas, and bubbles away. So this reaction is driven by Le Chatelier's principle, and by thermodynamics, it makes two really stable products, and it's entropically favored because you went from one thing to we went from two things, I guess, to three things. Okay, so these mechanisms are fine. You can definitely understand them, but your real focus here is on the reagents and the net transformations. So now that we know these reactions, let's go ahead and predict the products of these transformations. This time I have chiral alcohols. They're shown as single enantiomers. Although PBr3 does facilitate an SN2 on that alpha carbon of the alcohol, I do need to mention to you that this reaction will occur for primary, secondary, and tertiary carbons. So it would work on this alcohol, it would work on isopropanol, it would work on even T-butanol. I want to be clear, it will not though, work on, say, phenol, we do not have SN2 on sp2 carbons. No, no, no. Why? Well, sigma star CO, the one that you'd be attacking, it's in the middle of the ring. You cannot get there. So no, 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 no SN2 on sp2 carbons. But PBr3 will work even on tertiary while shocking alcohols. Okay, back to the regularly scheduled programming here. So we know that we're going to convert this alcohol into an alkyl halide. There is an SN2 at carbon, so it's going to occur with inversion. And we will obtain this secondary alkyl halide. You may be wondering, what is ether doing here? This is simply the solvent. And I've included it because it is included often in the book. Now we have a secondary alkyl bromide, and we have sodium iodide and acetone. So iodide is an excellent nucleophile, and acetone is a good solvent for SN2 reactions. So we have another SN2, and we would end up with this product. So we had one SN2 for inversion, and then another SN2 for inversion again. So overall, we have retention, right? We had a wedge and a wedge. So two SN2s was retention of stereochemistry because you had two inversions. Okay, now let's look at the second example. So PCl3, or again, most of my problems have thionyl chloride and with pyridine as a base because that is what a real synthetic chemist would use. But I want you to recognize both sets of reagents. So PCl3 will facilitate an SN2 on that secondary alcohol. SN2s occur with inversion of stereochemistry. Then we have cyanide. Yes, awesome. Excellent nucleophile and an SN2. So this may only be a fair SN2 substrate because it's secondary, but we have an excellent nucleophile that is not very basic. So we're not going to have E2. We're not going to have SN1E1. We are going to have SN2. And again, we see this thing, this observation where we have inversion and another inversion for net retention. This means that you started out with R and you ended up with R, right? The first SN2 went R to S, inversion. The second SN2, S to R. Another inversion for net retention. Let's work through these problems together. So for the first problem, we see we have a chiral secondary alcohol being converted into a chiral secondary alkyl halide. And we can see that this is happening with net retention of stereochemistry. It's S to S. So that tells me that we probably have two SN2 reactions. All right. So in other words, that means I cannot just treat it with thionyl chloride and pyridine because that will give me one SN2 with, that would give me one SN2 with inversion, and we need retention. Okay, cool. That also tells me I cannot treat with tosyl chloride and pyridine and then do an SN2 with chloride because that would give me the tosylate, and then treating with chloride would give an inversion, and I would still get the wrong enantiomer of product. So I really do need two SN2s. So let's think about how we're going to do that. What if we treated with phosphorus tribromide? This gives us an SN2 to give us the bromide, and then from the bromide, we treated with sodium chloride, or a second SN2, a second inversion, and net retention? Yes, that is a good answer. So let's do it. Excellent. And just know, the stereochemistry tells you what to do. So it has to be two SN2s. If it's one SN2, you're going to have inversion. If it's SN1, what would happen if we just treated it with HCl for an SN1? We would get racemization. So we would get the chloro out and the chlorosubstituent N as a racemic mixture. So we can't do SN1 either. It has to be two SN2s. Let's look at our second example. Our second example is a little more straightforward. We have inversion, so it's SN2. And we can do this now in one step with thionyl chloride, and we need to include pyridine. You need to include pyridine because remember I said that intermediate is the super strong acid and it has to be neutralized. So pyridine is essential there. Alternatively, you can use the reagent that is discussed in the book, PCl3. And then we don't need a second step. Super. So what do we have happening for the last example? We clearly have some sort of elimination because we're going from that chiral alcohol to an alkene. And then now we have a lot of choices. We have the most stable possible isomer of this molecule. So we could just brute force E1, no problem. We could also, if we wanted to, convert to the tosylate with tosyl chloride and pyridine. If you're afraid of E1 now, that's fine. I don't blame you. I'm afraid of it too. And then we can eliminate E2 with sodium hydroxide. Either way, but again, because we saw this was the most stable isomer of product, it was okay to do an E1, or we could do an E2 of the tosylate. That's pretty much it. There's no other options. Instead of making the tosylate, you could have made the chloride with SOCl2, or made the bromide with PBr3, and then eliminated that. Either way, it's okay. But the bottom line is you make it into a leaving group, and then you can do the E2. So we've just seen how we can use alcohols instead of alkyl halides in substitution and elimination reactions. We already knew this was possible for tertiary alcohols as long as they don't rearrange. By using HX, we could substitute the hydroxyl for the halide and make alkyl halides. As it turns out, we could also take alcohols again as long as they either don't rearrange or rearrangement was desired. We could treat them with sulfuric acid or concentrated phosphoric acid, and we could generate alkenes. But now we know, right, and I'm saying in place of alkyl halides because we have talked mostly about alkyl halides undergoing substitution reactions, right? So we're just making an analogy to alkyl halides. Nice chicken foot, huh? Okay, so now we've learned that alcohols can undergo SN2 and E2 as well, but the first thing that you have to do is make hydroxide into a leaving group. So a tosylate or an alkyl chloride or alkyl bromide. So to generate the tosylate, so make leaving group, we would treat with tosyl chloride and pyridine. To make the alkyl chloride, we would treat with thionyl chloride and pyridine base. Or you can make the bromide as well with PBr3. And then now from here, we can do eliminations, E2 eliminations, or we can treat with a nucleophile for an SN2. But first, you had to make hydroxyl a good leaving group. That really was the key of, or the point of making tosylates and making chlorides. So the alkyl halide and alcohols in these cases, they were standing in for the electron poor species in substitution and elimination reactions. So on the right side of the screen, I've posed a question, which is, can we use alcohols as the nucleophilic component of substitution reactions? And I think that in a way we know, yes, of course we can, we've done it. So we have used alcohols in SN1 reactions of alkyl chlorides. In this case, we use the neutral alcohol. If we use the alkoxide, we would just get elimination. So we don't do that. Make sure you use the neutral alcohol, the weak base. And for primary alkyl halides, we've been able to use alkoxides as nucleophiles in SN2 reactions. Okay, so yeah, we're cool with this. We can use alcohols as the electron poor species in place of an alkyl halide, or we can use alcohols as electron rich species in place of the nucleophile. We just have to pay attention and rely on our chemical intuition. Given that lengthy preamble, I would like for you to pause and propose a synthesis of the following ether. And I have a hint, you're going to use an SN2 reaction of an alkyl halide. Please pause. I'm going to teach you a way to think about synthesis problems, making stuff problems, a way of thinking that won a Nobel Prize. It is called retrosynthetic analysis. So I'm going to look at this molecule and I'm going to identify key bonds that I know how to make, and I'm going to think backwards. So what could I have made this from? So think backwards. Okay. Now for this ether, and the key is you have to identify functional groups. So the first thing you need to do is identify functional groups in the molecule. A couple of additional notes that I'll make here. I will be putting synthesis problems on every test for the rest of your life, as long as your life involves organic chemistry with me. And for each of these problems, you can solve it if you just identify the functional group and think backwards. So for ethers, the way that we think backwards is by breaking the carbon-oxygen bond. So we could have made this carbon-oxygen bond, or we could have made that carbon-oxygen bond. And those little squiggly lines mean bond disconnections. So we'll call these bond disconnections A and B, and we're going to think about what molecules or what reactions we could have used to make this ether based on each of these possible disconnections. Now, if we think about bond disconnection A, that was made from an alkyl halide. We'll use an alkyl bromide reacting with this alkoxide. Let's color code the molecule. So these atoms are in yellow, and these atoms here are in pink. And we can imagine that we have the bond between them forming like this to get to the product. Okay, what is that reaction called? Yes, it's called an SN2. And let's keep going with this. You cannot buy a bottle of just alkoxide. And so let's think about how you make the alkoxide. So to make the alkoxide, you take the alcohol and you need to deprotonate it. And when we want to deprotonate alcohols quantitatively, that means 100%. A really great base to use is sodium hydroxide. So sodium hydroxide is a strong base that is useful for quantitatively 100% deprotonating alcohols. Let's think about why that might be. So you take an alcohol, you treat it with sodium hydride. This is one of my favorite bases to work with when I used to be an actual chemist. And you're going to have an acid-base reaction. So hydride acts as the base. It's going to deprotonate the alcohol. And so you're going to end up with the alkoxide and certainly the sodium counterion as the conjugate base. And then hydrogen gas is the conjugate acid, right? So first of all, if we want to think about the equilibrium constant, that's 10 to the pKa of the product acid minus the reactant acid. So the reactant acid has a pKa of 16. The product acid has a pKa of, I don't know, super high. How do you deprotonate hydrogen? Plus it's a gas. You can look up numbers and they're going to vary, but let's say that it's 50, okay? So if it's 50, which I think is a reasonable number, that's around the same as an alkane, which seems like a reasonable comparison, then the equilibrium constant for this reaction is 10 to the 50 minus 16, or 10 to the 34. Excuse my slow math. So that's huge, meaning that the products are heavily favored, plus the conjugate acid is a gas, it evolves, it bubbles away. So Le Chatelier's principle also drives this reaction. So bottom line here, sodium hydride is an awesome base for deprotonating alcohols. So disconnection A, we're going to start with this alcohol, which represents these atoms. We're going to deprotonate it to make it into an excellent nucleophile. We're going to treat it with this electrophile, this alkyl bromide, and have them react by an SN2 to make, so they're going to make this bond here, bond A, right? Now we'll evaluate, well, let's evaluate it now actually. So do you think this is a good SN2? It's not. So we have a secondary alkyl halide. That's a fair SN2. And we have an alkoxide base. That's a strong base. So that's a good E2. Uh-oh. So this proposed reaction, it's not going to lead to the ether. It is going to mostly lead to an alkene byproduct. Well, I had to reorganize that slide a bit, but now I'm back, and this is the point, right? This proposed SN2 to make bond A in this ether, it would not be the best choice because that particular SN2 would only be fair because we have a secondary alkyl halide, but it would be an awesome E2 because alkoxides are strong bases. So our major product, like I said, would be the alkene. Okay, bummer. So that's not going to be the best choice, right? But that's no big deal because we have another bond that we can think about disconnecting, and that is bond B. So let's do that. So if we break bond B, then we're proposing that we're going to be using this alkoxide and an alkyl halide that looks like this. Let me label the atoms for you. So here are those two carbons. Here's the oxygen. Oh, we can do the oxygen. And what are the oxygen? Yeah. There are those three carbons, and then of course this is the oxygen of the ether. So now this time we're going to be making, again, bond B, and we're going to be making it by an SN2, displacing the bromide. So how does that look to you? Yes, that should look good. And this is going to be a good SN2 because we have a primary alkyl halide. This carbon here is primary, so this is a good SN2. And then how do we make the alkoxide? Well, we make it from the alcohol by deprotonating with sodium hydride, just as we discussed before. Okay, super, this is a mess. And the nice part is we figured out this is the correct reaction pathway. How do we write our answer on the test? That's all we care about, right? Well, your answer to synthesis problem should look like this. Starting materials, conditions, some intermediate that you would isolate in lab, so your final product for that step. And then if you do something new to it, then more conditions, and then your final product. You do not want to write any mechanisms for synthesis problems. No mechanisms. Of course, when I was thinking, I thought about mechanism because that helped me choose the best path. That was B. But when I write my answer, I don't write mechanisms. So here's what we discussed. We're going to be disconnecting this bond, bond B. It's going to be made from this alkoxide, and the other two carbons are made from this alkyl halide. So we'll call the carbons 1 and 2, X, Y, Z. Okay. And that was our key step. We can make ethers by substitution. So for our answer, we're going to generate the alkoxide from the alcohol, deprotonate with the strong base sodium hydride, make the alkoxide salt. This will be our electron-rich species for our E2, for SN2. And here's our electron-poor species for our SN2. And we'll generate the ether. All right, fun. Now, this seemed, I don't know what it seemed like to you, but this is a pretty important reaction, and it even has a name. It's called the Williamson Ether Synthesis. And yes, I am for real, but it is not that Williamson. It is some other Williamson. The Williamson Ether Synthesis is an example of a named reaction, meaning that it's some reaction given a person's name, Williamson. Usually the person who discovered it, or if the person who discovered it was a graduate student, it's whoever lab they worked in as a graduate student. Now, it has a fancy name, but it is just an SN2 reaction in a specific context, and that specific context is making an ether. You need to recognize the Williamson Ether Synthesis both by name and if you just see the reactants and products. You start with an alcohol, which has a pK of 16. You deprotonate it with sodium hydride, 100% deprotonation, right? We saw the equilibrium constant was a gazillion. It was much, 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 much greater than 1. That generates an alkoxide, an electron-rich species. Treat that with an alkyl halide, which must be a good SN2 substrate. Usually that means primary. And then you will make an ether. Good. Now that you've got down the generic reaction, let's go ahead and propose a synthesis. So propose a synthesis of each of these molecules using only alcohols as your starting materials. Ready, set, go. Now, these are ethers. And so remember, step 1 is to identify the functional group. And then step 2 is to think about the possible bond disconnections. So you can disconnect here. And if you do that, then oxygen, that's the nucleophile. This carbon, that is the electrophile, meaning it's the alkyl halide. So that bond disconnection would give us something that looks like this. Okay, orient yourself to that, please. And then, of course, you could also investigate, say, that bond disconnection, where you would have this alkoxide and this alkyl halide engaging in an SN2 reaction. All right. So that's what you need to do here, and if you didn't, you have one more chance. And same with the other ether, there's 2 possible bond disconnections. All right, last chance. So I have both of the bond disconnections written out for both ethers. And let's just take a look. So let's look at bond disconnection A for this first molecule. So for bond disconnection A, we're breaking this bond, so that carbon is going to be the alkyl halide. So that carbon right here. And you need to make sure that it's going to be a good SN2 substrate. So this is a primary alkyl halide. So that's a good SN2, right? Now we could think about the other bond disconnection B. That's this carbon would be the alkyl halide. That's this carbon right here. And that's also primary. So both of these disconnections, both of these proposed syntheses are okay. So either answer, A or B, would be correct if we were doing this example on an exam. So take a look at that. Now the second molecule is a little more tricky, and that's for a couple of reasons. So if you look at the two carbons that are directly bonded to oxygen, the pink one, that's primary. So we know that disconnection B should be good to go because the alkyl halide that we would react it with is primary, and that involves a good SN2. Now the yellow carbon, it is not only secondary, but it is also an sp2 carbon. This carbon here, that is an sp2 carbon. Under no circumstances, none whatsoever, should you propose SN2 on sp2 carbons. No, 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 no. No SN2 on sp2 carbons. I don't even care that it's secondary. That's not the point. The point is the sp2 part. Think about the frontier molecular orbitals for an SN2 reaction. You have the non-bonding orbital of the nucleophile attacking sigma star CBr. Where is sigma star CBr for this carbon? It is in the middle of this ring. How are you going to get the nucleophile in there? You're not. Don't do it. Please do not do it. It has a nice catchy ring to it. No SN2 on sp2 carbons. Period. Forever and always. So for this particular molecule, the only possible route is route B. Route A will not work. Do not do it. You can only use route B. So when you have, let's take a quick time out. So when you have one carbon bonded to the ether as primary and then the other that's secondary or sp2 or tertiary, you want to pick the bond disconnection that involves the primary carbon as your alkyl halide. Awesome, now we have another chance. So let's try this molecule. All right, this is an ether, so we have two choices. We can disconnect this bond, call this bond A, and we can disconnect this bond. I will call this bond B. To bond A, we have a tertiary carbon. To bond B, we have a primary carbon. So which of these disconnections do you think would be better for an SN2? I agree. It would be bond B. Be bond B. I'm sorry, I don't know why I think that's so funny. It would be bond B. And that is because if you disconnect it bond B, you have a primary alkyl halide, which is good for SN2. So you could generate the alkoxide by deprotonation of T-butanol with sodium hydride. And then you'd be proposing that sodium T-butoxide is your nucleophile, your electron-rich species, the alkyl halide is your electron-poor species, and you would undergo an SN2 to get the product. Okay, cool, awesome. No, not awesome. There's a problem with this. What's that problem? Yeah, so this is a bulky nucleophile. And it's really a bulky base. And this oxygen is just surrounded by these methyl groups, and it cannot get in to do that attack. So instead, this is going to favor an E2. So you're going to have no SN2. You'll just have an E2. So actually, if you combine these two species together, you're just going to get ethylene and T-butanol. So that's a bummer, okay? That's a bummer. Because we picked the right disconnection, but it's still not going to work. So is there another way to do this? Yeah, you're going to hate me, but it's actually bond disconnection A. And so you might say, well, no, it can't be, right? You just cannot do an SN2 on this. It's tertiary. Correct. But what can you do? Oh, you can do SN1. So you want to take the alkyl bromide. And now if you're going to do an SN1, do not use the alkoxide. No, no. That will do an E2. It's a strong base. What do you use? Yeah, you use the neutral alcohol. So we're going to use the neutral alcohol, ethanol, for an SN1. Okay. Ethanol, 2 carbons. That's all of this. Bromide leaves, right? But no mechanisms in a synthesis problem. I'm just pointing it out to help you think about what's happening here. Okay, good. Got to use the neutral alcohol for an SN1. Excellent. What have you learned about making ethers? Take a moment, brainstorm, write it down. This is my summary. And the real key is that you need to look at the substitution of the ether, particularly the carbons bonded to oxygen. When both of those carbons are primary, this is the luckiest day of your life because either bond disconnection will work just fine. And we saw that somewhere, my friends. We saw that for this molecule here. Disconnection A and disconnection B, they were both fine. You could use the SN2. Now, when we have one of those carbons is secondary, that takes it up a notch, right? So then we can only do bond disconnection A when one of those carbons is secondary. And then finally, when we have one of the carbons tertiary, we need to use an SN1. And that's the bottom line. Live it, learn it, love it. Excellent. Now we're going to move on to amines. So pause and answer this question. I have drawn here a primary amine. And for amines, the primary actually refers to the number of alkyl groups on nitrogen. So everywhere from no alkyl groups, ammonia, to a quaternary ammonium salt, which has 4 alkyl groups, it will have to have some anion, counterion, since it will certainly be a salt with a formal charge on nitrogen. Now for the primary amine, the highest energy filled molecular orbital will involve that non-bonding pair of electrons on nitrogen, and the LUMO will be sigma star Cm. So if we think about how these molecules might behave in substitution and elimination reactions, it's kind of unclear like why we'd even be talking about this, right? Because there's just no way that we get a substitution. This seems crazy. Why does this seem crazy? Well, we need to evaluate, is this a good leaving group? How do we do that? We're going to look at the conjugate acids pKa. Conjugate acid of amide is ammonia. Ammonia has a pKa of 35. So what do you all think? Is that a good leaving group? No, no, no. It's an awful leaving group. So SN2 doesn't happen here, and SN1 wouldn't happen either. But you might say, hey, this is a pretty good donor, and it is. And so we could certainly see amines not acting as the electrophilic partner in a substitution, but acting as the electron-rich, the nucleophilic partner in a substitution, and reacting with, say, some alkyl halide, and after deprotonation to form an amine. So from primary to secondary. Okay, so we have some SN2 reaction here. So certainly they could be the electron-rich component, the nucleophile. We're going to think more about that in just a second, but let's just summarize. We know that amines are actually basic, and amines can be nucleophilic. All right, let's go ahead and predict what the products of the following reaction. Well, we have an amine and we have an alkyl halide. And when you see an alkyl halide, I would really like for you to immediately label it as electron poor or electrophilic. Same thing. We know that it's electron poor species use their accept orbitals. Its LUMO or accept orbital is sigma star CBr. Amines are electron rich, or they are potential nucleophiles, in other words. And their donor orbital, the highest energy Fill molecular orbital, is that non-bonding pair of electrons on nitrogen. So we can certainly expect the amine to react with the alkyl halide in an SN2 reaction. So what do you think the product is? Go ahead and predict if you have not already. Okay, so certainly we have that first SN2. That will generate this protonated secondary amine, the pKa of which is what? What is the pKa of ammonium? Correct, 9. So we will have another molecule of amine and deprotonate it in a proton transfer reaction to lead to a secondary amine. Is that where we stop? Unfortunately, no. Secondary amines are even more electron rich than primary amines, and that's because alkyl groups are electron donating by hyperconjugation. EDG, electron donating group. So, if alkyls donate electrons, this secondary amine is even more electron rich than the primary amines. So what do you think it does? Yes, it keeps reacting like this. So that secondary amine is going to react with yet another molecule of the alkyl halide in an SN2 reaction to generate this protonated tertiary amine, which will become deprotonated by another molecule of the amine acting as a base to generate this tertiary amine. Do you think we are done? Nope. Alkyl groups are electron donating. So guess what? This is even more electron rich, even more nucleophilic than secondary and primary amines. So the tertiary amine keeps reacting. It reacts again with another molecule of the alkyl halide to finally, mercifully, generate the quaternary ammonium salt. So you might think, well, that was useless. I mean, you're mostly correct, but we're going to see two applications of this reaction. So first, sometimes in lab and, not this semester, but we'll see these quaternary ammonium salts used as phase transfer catalysts. Phase transfer. That means between the aqueous and the organic. So as you can imagine, the quaternary ammonium salt, it's a salt, it's soluble in water, but it's also soluble in organic solvents because it has this huge, greasy, all these alkyl chains. It's very greasy. So it's soluble in both, and it can pull molecules in from the aqueous, from the organic into the aqueous, and we can use them as catalysts for what's called phase transfer reactions. So stay tuned for Chem 12B for that. But for today, we're going to look at a reaction called the Hoffman Elimination that applies this idea, where we will fully alkylate. Alkylate means add alkyl groups. We will fully alkylate amines. So go ahead and predict the product of this transformation. I know, friends, this is a long and painful video. It is almost over. So we're going to have just complete alkylation. So nitrogen can make 4 bonds. It will have a positive formal charge if it is making 4 bonds, but it can make 4 bonds, and so you're going to make all 4 bonds. We have 3 methyl groups, and then this alkyl group, it is making all 4 bonds. So completely alkylate the nitrogen to make the quaternary ammonium salt. You should certainly draw the mechanism yourself. It is identical to this one, so I am not doing it again. Now, so what? Well, when you take that quaternary ammonium salt, which drawn out looks like this, and you treat it with silver oxide, I know it's crazy, but you do, treat it with silver 1 oxide, what happens is you get an alkene. You observe an alkene. And it's not just any alkene, right? It is, yep, it is the less substituted alkene. Hey, it's the kinetic product. We don't have too many ways of isolating this product. We mostly are able to isolate the thermodynamic, the most stable alkene product. But we're able to get it here. Now, you might wonder why? Why is this? Well, you can read about it in the book. Since we're at an hour and 10 minutes, I'm not going to belabor it right now. But basically, the bottom line is this group is huge. So, hydroxide, which is generated under these conditions with silver oxide and heat, it just deprotonates the least sterically hindered proton, the one that is easiest to get to. Which in this case is this beta carbon here. It's the primary beta carbon, not the secondary one. So we see deprotonation there to get the less stable kinetic product of the alkene. Okay, so how can we explain the difference in regioselectivity? This is huge and it blocks this beta carbon. And so you're going to deprotonate here to get the less stable, the less substituted alkene. Again, if you want the totally sophisticated explanation, please feel free. Look it up. Here's your reference. But it's okay. This is good enough. Now, and again, and this is generating, when you heat up the silver 1 oxide, it's generating hydroxide here. So that's what's doing the elimination. So this is simply an E2. It's an E2, and I probably should have mentioned this on the previous page, but I'm just wanting this video to be over so much that I didn't. I'm sorry if that was too honest. I'm sure you want it over too. It generates this amine leaving group, and this is an awesome leaving group. It's a totally stable molecule. So it's a totally stable molecule. It's a great leaving group. It is not a terrible leaving group. Like when we were first thinking about these reactions, we said if you eliminated NH2, that would be awful because it's the conjugate base of a weak acid. But ammonia is a totally stable molecule, right? And amine is just a totally stable molecule. So it's a great leaving group. So this is why partially why this elimination occurs. And then this is just so huge, you get the less substituted alkene. Meanwhile, if you had just taken the equivalent alkyl bromide and treated it with hydroxide, you would get formation of the more stable product. And that's because hydroxide is super small. Bromide is relatively small. It's not, but like this is a long bond, and so it's easy to get into either position. And it just makes the more stable product, which is the disubstituted alkene. The point of this slide is that the Hoffman elimination, so starting out with an amine, making a quaternary ammonium salt, and then eliminating. The only reason we're talking about this is because it makes the less substituted alkene. The only other way that you know how to do that is with potassium T-butoxide. So I told you that you could maybe make the less substituted alkene from the alkyl halide if you used a bulky base. For the Hoffman elimination, instead of a bulky base, you have a bulky leaving group, and you still favor elimination here at this less sterically hindered proton. All right, you got to do it on your own. You're going to make a reaction chart. You'll have some instructions about that on Canvas. Why are we learning this? I've already explained it. You're making the less substituted alkene. E1, we'll make this one. E2 with hydroxide, we'll make this one. So Hoffman and elimination with T-butoxide are the only ways to make the less substituted alkene. That's why we're learning it. Summarize, and then revisit the learning goals. Okay, I am so sorry that this has been really long. I like to go into details so that you can, I don't know, I want you to understand what's going on. So now it's time to practice.